So, good evening. So we will be starting inverse Laplace transforms today. So we have been discussing Laplace transforms. Now we have to discuss inverse Laplace transform because together using both Laplace and inverse, we solve the differential equations. So now the basic definition here. If Laplace transform of a function is, we know how is it defined. It is 0 to infinity e power minus st f of t dt, and this we get as a function of s. So f bar is a Laplace transform. So then f of t is Laplace inverse of f bar of s. So this is called as the inverse Laplace transform. Inverse Laplace transform of f bar of s. So f of t is called as the inverse Laplace transform of f bar of s. So now we have had a list of Laplace transform formulae. So now we have to just make a list of the inverse Laplace transform formulae and the properties. So first, the list of standard inverse transforms. So list of standard inverse transforms. First, Laplace inverse of 1 upon s. We know Laplace of 1 is 1 upon s. So Laplace inverse of 1 upon s is 1. Then Laplace inverse of 1 by Sn, 1 by s power n. We know that Laplace of t power n is n factorial by s power n plus 1. This what we know. Now we are wanting 1 by s power n. So let us reduce this. Laplace of t power n minus 1 will be n minus 1 factorial by s power n. So this is Laplace of, you can divide both sides by n minus 1 factorial, and because n minus 1 factorial is a constant, it can go inside the Laplace. So this is nothing but 1 by s power. So therefore, Laplace inverse of 1 by s power n will be t power n minus 1 by n minus 1 factorial. Okay. Just manipulation of this, or another way to write this is Laplace inverse of 1 by s power n plus 1 will be t power n by t power n factorial. Okay. So the power of t and the factorial below will be 1 less than the power of s in the denominator. Okay. So I'm erasing this part now. From the list. Next, Laplace inverse of 1 by s minus a. We know that this is the Laplace 1 by s minus a is the Laplace transform of e power at. Now, Laplace inverse of 1 by s minus a whole power n. If you remember, whenever we multiply a function with e power at and then do a transform, the transform changes by replacing s by s minus a. So now for the inverse, the same thing. This function 1 by s is t power n minus 1 by n minus 1 factorial. So if it is 1 by s minus a, it is e power at into t power n minus 1 by n minus 1 factorial. Just this multiplication with e power at replaces s by s minus a. So therefore the inverse transform, when we have s minus a instead of s, then surely we will be getting x in the function a factor of e power at. Next, Laplace inverse of 1 by s square plus a square. Now a by s square plus a square we know is sine, Laplace transform of sine of at. So this will be sine of at by 1 upon a into 1 upon a. 1 upon a times sine of at. So Laplace transform of the right hand side will give us 1 upon s square plus a square. Therefore, the inverse transform, inverse Laplace transform of 1 by s square plus a square is 1 by a sine at. Similarly, the Laplace inverse of s by s square plus a square. This is cos at. And then Laplace inverse of 1 upon s square plus s square minus a square. This is 1 by a sine hyperbolic at. This we have done. The Laplace transform of sine hyperbolic at is a by s square minus a square. Next, Laplace transform of s by s square minus a square. This is simply cos hyperbolic at. Next, Laplace inverse of 1 upon s minus a the whole square plus b square. So look at this. If it is s square plus a square, it is 1 by a sine at. Now this 1 by say s square plus b square. So it will be 1 by b sine bt, but s is replaced by s minus a. So definitely in the function you will have e power at term, and this is sine bt into 1 upon b. So the same formula, just that s is replaced by s minus a. Next, Laplace inverse of s minus a upon s minus a the whole square plus b square. Okay. This is e power at cos bt. Next, Laplace inverse of sin 1 upon s minus a the whole square minus b square. Now instead of plus, it's a minus. So it is sine hyperbolic. So we get 1 by b sine hyperbolic bt, but s is replaced by s minus a. So there has to be a factor of e power e raised to et. E raised to 8. Next. Now Laplace inverse of s minus a upon s minus a the whole square minus b square. This will be e power at cos hyperbolic bt. Okay. Now after this, some more standard results. This is important to remember. It will be easier, although it is derived. This is s by s square plus a square the whole square. Say multiplication by t. If you remember the Laplace transform formula, yeah, a multiplication by t means you differentiate. So if I multiply the function once with t, I differentiate the Laplace transform once with a minus sign. If I multiply with t power n minus 1 to the power t power n and nth derivative of the Laplace transform of the original function. So multiplication of t gives us that. So now let us look at this result. Now 1 by s square plus a square, or a by s square plus a square is sine. Laplace transform of sine at is this. So this is f bar s. I'll erase this, but I'm just showing the proof. So now Laplace transform of t sine at is minus d by ds of f bar s, that is a by s square plus a square. So this gives us the derivative will be minus a upon s square plus a square the whole square into 2s. So you get 2as plus 2as upon s square plus a square. So now if we do an inverse, t sine at will be Laplace inverse of 2as by s square plus a square the whole square. So this 2a, we can bring it out and bring it to the denominator this side. So we get this Laplace inverse of s by s square plus a square is 1 by 2a t sine 80. That's what it is. Okay. So I'll erase this. So we derived in the reverse manner. We have done this proof earlier. I didn't just want to copy it. I wanted to show how we get it. Next. So this one is a little difficult one because t is involved here. But we should remember these results. Now this is a little more difficult, but 1 by s square plus a square the whole square. Now this is 1 by 2a cube sine 80 minus 80 cos 80. Okay. Although, we can derive this, but this is a standard one to remember. These are very important to remember. Others by logic we can get it. This one we have to memorize. And Laplace inverse of s square minus a square by s square plus a square, the whole square. This is t cos 80. T cos 80. So take cos 80 and do its derivative. Cos 80 is s by s square plus a square. Differentiating this once with a minus sign, you will get this minus of s square plus a square whole square to s square plus a square into derivative of s, that is 1 minus s times 2s. So okay, we get minus of s square minus 2s square is minus s square plus a square. So we get this. So this is Laplace transform of t cos 80. Multiplication with t. So we get this. So these 15 we must commit to memory. These are 15 we have to commit. Just like your derivative and integral formula, we need to commit this to memory. So all right, we'll do certain problems based on simple results and then move on to further. Okay. Find the Laplace inverse transforms of the following. First, 1 by s square plus s. So f bar of s is 1 by s square plus s. So this is 1 by s into s plus 1. And this 1 we can write as s plus 1 by s plus 1 minus s divided by s into s plus 1. So we get 1 by s minus 1 by s plus 1. So the given function is this. Therefore, Laplace inverse of this function will be the Laplace inverse of 1 by s minus the Laplace inverse of 1 by s plus 1. This is 1 minus, this one is e power at if it is s minus a. So a is minus 1 here. So e power minus 1 times t. So this is the Laplace inverse. Okay, just a simple formula. Next, let us find the Laplace inverse of s cube plus s square. So we need to find this. Similarly, we will have to do that f bar of s is 1 upon, now I will write directly s plus 1. So now we have to resolve this into partial fractions. Now how to resolve this? So we can have a by s plus b by s square plus c by s plus 1. Okay, this is resolving into partial fractions. So when we do this, the numerator, we have to equating the numerator 1 is equal to a into s plus 1 plus b into s plus 1 plus c into s square. Okay, so now we need to equate this both sides. So this implies the numerator 1 is a plus b times s square. Now, then taking the coefficients of s, we have a and b. So we have a plus b times s. Then look at the constant. We just have b. Oh, this is, sorry, this is c. This is a plus c times s square and a plus b times s plus b. All right, collecting coefficients of s square, collecting coefficients of s and the constant. Now comparing the left hand side and the right hand side, this gives us b equal to 1. This gives b equal to 1. And a plus b is equal to 0, which implies a is equal to minus b, which is equal to minus 1. And then a plus c is equal to 0, because coefficient of s is 0, coefficient of s square is 0, and the constant term is equal to 1. So b equal to 1, a plus b is 0, a plus c is 0. So c is minus a, which is minus of minus 1. So we get b equal to 1, c equal to 1, and a is minus 1. Therefore, this f bar of s is minus 1 by s plus 1 by s square plus 1 by s plus 1. 1 by s plus 1. Okay. So now Laplace inverse of this is Laplace inverse of the first term, Laplace inverse 1 by s square plus Laplace inverse of 1 by s plus 1. So this is Laplace inverse of minus 1. Minus comes out. Laplace inverse of 1 by s is 1. Then this one is t power 2 minus 1 by 2 minus 1 factorial. The second term. The last one is s minus of minus 1. You have s, the e power at, a is minus 1. So you get this. Therefore, this is Laplace inverse of this is t. This is minus 1 plus e power minus t. Okay. So this is how we do. It requires just practice. It is just a matter of decomposing the given expression into known forms. If we do into known forms, and after that, we just have to apply the formula. Third one, this may be much easier. So find the Laplace inverse of s square minus 3s plus 4 upon s cube. This is very, very easy, direct. So the solution, f bar of s is this function. Divide by s cube, you get 1 by s minus 3 by s square plus 4 by s cube. This is very, very simple. So Laplace inverse of this one will be Laplace inverse of 1 by s minus Laplace inverse of 3 times Laplace inverse of 1 by s square plus 4 times Laplace inverse of 1 by s cube. So 1 by s is 1 minus 3 into t power 1 by 1 factorial plus 4 into t square by 2 factorial. So we get 1 minus 3t plus 2t square. This is the Laplace inverse of this function. Now these were very simple. Let's move to little difficult problems. Slightly increasing the difficulty. This is s plus 2 by s square minus 4s plus 13. So let's look at the solution. Now f bar of s is s plus 2 by s square minus 4s plus 13. Okay. So now we need to simplify this. Look at the denominator. We can write this as, observe carefully, this is minus 4s. So we can consider this as s minus 2 the whole square. So s minus 2 the whole square gives s square minus 4s plus 4. That 4 plus 9 gives 13. So this 9 will be replaced by 3 square. So denominator is s minus 2 plus 3. S minus 2 whole square plus 3 square. Now this is s plus 2. Now to convert to standard forms, what we will do, we will write this as s minus 2 plus 4. This plus 2 can be written as minus 2 plus 4. So we get this. Now we can split into partial fractions. So the first term divided by the denominator, we get s minus 2. S minus 2 the whole square plus 3 square plus 4 upon s minus 2 the whole square plus 3 square. Now this is f bar of s. Therefore Laplace inverse of this given function is same as the Laplace inverse of the first term plus 4 times the Laplace inverse of the second term. Now these are in standard forms. First one is directly e power at. S is replaced by s minus a. So a is 2. So e power at will be e power 2t times cos 3t. Okay. S minus a whole square plus b square. So for sine, what is the formula? For sine, the Laplace you get for sine is you will get 3 on top. 3 by s minus 2 the whole square plus 3 square. Now instead of 3 is not there, so you multiply and divide by 3. So you'll get 1 by 3, 4 into 1 by 3, e power 2t sine 3t. Just applying this formula. If we see in the list, this one, 1 by b e power at sine bt, the ninth formula. When we apply, we get this. So this is the inverse transform. Okay. Now next, two s square minus 6s plus 5 upon s cube minus 6s square plus 11s minus 6. So clearly, this function has to be split into partial fractions. And there's an interesting, you can just observe this and tell something. If roots are 1, 2, and 3, sum of roots is 6. Sum of the product of the roots taken one at a time. So 1 into 2 plus 2 into 3 plus 3 into 1. What do you get? 6 plus 2 plus 3, 11. And the product of the roots is 6. So this is s cube minus sum of the roots times s square plus sum of the product of the roots taken in pairs, plus the minus the product of the roots, all the three roots. So this I'm directly writing here. Otherwise, you will have to simplify this. This is of the form s minus 1 into s minus 2 into s minus 3. This is the factors. How did I see? It is not that I just saw the coefficients and that I got an idea. Generally, for any polynomial equations, there's a trick. For any polynomial equation, say x power n, the coefficient should be 1. That's all. Plus, say a1 x to the power n minus 1 plus a2 x to the power n minus 2 plus a3 x to the power n minus 3, so on, an. What happens is a1 will be sum of the roots. Actually, it should be minus, because usually it is minus sum of the roots will be minus the coefficient of this upon the coefficient of the highest term. So minus b by a, we say, na? So from that, so this is minus. A2 will be minus 1 the whole square. Sum of the products of roots taken two at a time. Product taken two at a time. A3 will be minus 1 the whole cube into sum of the products of the roots taken 3 at a time. Like that, an is minus 1 to the power n. Now, there will not be sum of the products because product of all the roots, the last term will be product of all roots. The previous term will be sum of the products of the roots taken n-1 at a time. So you will get two cases. So this is something that you should remember. It will be very useful in problem solving. So here I save time. I'd save time just looking at it, and directly I wrote the factors. Otherwise, it would be very, very difficult. We'll have to, by inspection, find one root and then factorize it out and then find the roots of the remaining quadratic. So now, so this becomes, so again, I'll write this here, f bar s 2s square minus 6s plus 5 divided by s minus 1, s minus 2, s minus 3. So you get a by s minus 1 plus b upon s minus 2 plus c upon s minus 3, because all are linear factors. If they were not linear factors, then we'll have to consider. So equating the numerators now, if you bring it to the common denominator, the numerator will be a into s minus 2 into s minus 3 plus b into s minus 1 into s minus 3 plus c into s minus 1 into s minus 2. What did I do? I have to equate this with this partial fractions. So I bring this to the common denominator and I get a into s minus a into these two factors, b into these two factors, c into these two factors. Now substitute s equal to 1. If you substitute s equal to 1, this term cancels. You get 2 into 1 minus 6 into 1 plus 5 is a into 1 minus 2 is minus 1. 1 minus 3 is minus 2. So we get this is 5 plus 2 is 7 minus 6 is 1, and this is a into 2. So we get a is 1 upon 2, half. Now substitute s equal to 2. If we do s equal to 2, see what happens. 2 into 2 square minus 6 into 2 plus 5 gives a times 0 plus b times 2 minus 1 is 1. 2 minus 3 is minus 1 plus c times 0. So b is minus 1 here. So b times minus 1. So 4 2's 8. 8 minus 12, or 8 plus 5, 13 minus 12 is 1, is minus b. So b is equal to minus 1. Now put s equal to 3. So we get 2 into 3 square minus 6 into 3 plus 5. So substituting s equal to 3, a factor will be 0, factor of b product will be 0, plus c into 3 minus 1 is 2 and 3 minus 2 is 1. So 2 into 1. Now let us see, this is 9 2's 18. So 9 into 2, 18. And this is also minus 18. So 18 and 18 cancels. You're left with 5. 5 is equal to 2c. C is equal to 5 upon 2. All right. So now, therefore, f bar of s is a upon s minus 1. A is half. So half upon s minus 1. B is minus 1. So minus 1 upon s minus 2. And C is 5 upon 2 s minus 3. So now we simplify. We apply the Laplace inverse. So half Laplace inverse of 1 by s minus 1 minus Laplace inverse of 1 by s minus 2 plus 5 by 2 times Laplace inverse of 1 by s minus 3. So this is 1 by 2 times e power t, right? E power at. And this is minus of e power 2t plus 5 by 2 to e power 3t. So this is your result. So problem did not involve any complex Laplace transform. It was very simple. What we had to do is to resolve this into partial fractions. Okay. And knowing the basic concepts of polynomials, we could do it very fast. That's all. Next. I am purposely taking time and doing this because we get a lot of problems on inverse transforms. And more than direct forward Laplace transform, we get on inverse transforms. So s by s power 4 plus 4 a power 4. Okay. Solution. F bar of s is s by s power 4 plus 4a power 4. Now, this is not any standard result. From this, we have to move towards a standard result. So we have to bear these standard results that we looked up here, these in mind. We have to bear this in mind and move our simplification to get in one of these forms. So now let us look how we can simplify. This is s by, I will write this as s square the whole square plus this is 2a square the whole square. Okay. Now I will add a term and subtract a term. I will add plus, this is a square plus b square. So I'll add 2ab. 2ab will give me 4. 2 into 2 for a square s square. So because I've added this term, I will subtract this term. So I get s upon s square plus 2a square the whole square minus 4, so 2as the whole square. 4a square s square is this. Now this is a plus b into a minus b. So I get s upon s square plus 2a square plus 2as and s square plus 2a square minus 2as. Now, if I multiply and divide, see, if I make a difference of these two factors, so s square plus 2a square gets cancelled. I have 2as plus 2as, it is 4as. So if I multiply and divide by 4a, numerator I get 4as. So the numerator, now 1 by 4a, this 4as, I can write as s square plus 2a square plus 2as minus s square plus 2a square minus 2as upon the product of these two factors. So next, what I do now is split into fractions. So I get 1 by, now I'll split this in a interesting manner. This is, I'll write in the next step anyway. I'll further simplify this by 4a. Now I'll remove 1a square aside. I have s square plus a square minus 2as. That will be s minus a the whole square plus a square. Now this I have got into one of the standard forms. Minus, then 1 upon s plus a square, s plus a the whole square plus a square. So this is my result. Now just see, initially it appeared very strange, this expression. How can we convert? But just adding and subtracting this term 4a square s square, we could resolve this into two factors and split this into partial fractions very neatly. And now we have got into the standard forms. So we have this standard equations here. This one 1 by s minus a whole square plus b square. So here it is a square only. So you'll get 1 by a e power at sine at. So let's do that. So Laplace inverse of this is 1 by 4a times Laplace inverse of this expression. In exam, you don't have to write these steps directly, you should do. But because I'm teaching and this will be a reference for you to follow later, I'm doing this. You should, in fact, these, if you are practiced, from here, you should be able to jump here. And from here, maybe jump here and directly you can come here. If you are well practiced, you can skip steps. Now this is 1 by 4a into. Now I get this as 1 by a e power 80 sine 80 minus, what do I get here? Instead of s minus a, I have s plus a, which is s minus of minus a. So s minus of minus a. So I get 1 by a, this factor here, and e power s minus of minus a. So e power minus 80 sine 80. So we get 1 by 4a square e power 80 minus e power minus 80 into sine 80. Now you multiply and divide this by 2. What is a sine hyperbolic 80? Is e power 80 minus e power minus 80 by 2. So e power 80 minus e power minus 80 is twice of this. So you get 1 by 2a square. This 2 goes here. Sine hyperbolic 80 into sine 80. This is the answer. Simplified this way. Okay. Let's move to another problem. So we can see inverse Laplace transform is little just like differentiation as a procedure, and for integration we need to remember the formulae for differentiation and try to fit the given integrand into the known antiderivatives. So that process is little more difficult than differentiation. So integration process is more difficult than differentiation. Similarly, the inverse Laplace transform, we have to be thorough with the Laplace transform formulae and all the properties, then we can do the inverse Laplace transform. So that's what it is involved. So the next question. So find the inverse transform of 5s plus 3 upon s cube. Just a second. Plus s square plus 3s minus 5. Okay, so this is the function. Now how to solve this one? Now sum of roots are not so easy as 1, 2, 3 like the previous case. We don't know the roots. So first thing is we need to check some p of s. The denominator is a polynomial. So we need to check what is the root. Now you put s equal to 1. So p of 1 is 1 cube plus 1 square plus 3 into 1 minus 5 is 0. Therefore, s equal to 1 is a root. Therefore, which means s minus 1 is a factor of this polynomial in S. So this denominator, polynomial in S, we can write this as a factor s minus 1. Now, this s cube plus s square plus 3s minus 5, we have to now factorize as s minus 1 and just find the remainder. How do you find the remainder? Just check. Coefficient of s cube is 1. So coefficient of s square will be 1. So s into s square will give you s cube. Then constant term is minus 5. Constant term is minus 5. So minus 1 into some number should give you minus 5. So obviously that number is plus 5. So you have found the first term and the last term through the coefficients of s cube and the constant. So s cube and minus 5 you get. Now you have to check the intermediate terms. You take s square term. So here you have to get a coefficient for s, some number. So now s square is 1. Here minus 1 into s square gives minus s square. So you have to get plus s square. So minus s square plus 2s square will give you plus s square. So this has to be 2. So you get 2s square minus s square will give you plus s square. So we have found this. So now I have to check whether this is correct. So we have equated this coefficient, we have equated this coefficient, then we equated this coefficient. So to test whether this is right, we have to check whether coefficient of s is 3. So let us do 5 into s into 5 is 5s, and 2s into minus 1 is minus 2s. So 5s minus 2s gives us 3s. So this coefficient is also correct. So we have split this into this. Now incidentally, just by observation, we can say that this cannot be factorized further. Why? See the discriminant. B square is 4, minus 4ac is minus 20. So 4 minus 20 is minus 16. So discriminant is negative. So it cannot be factorized further. So now coming to f bar s. So we have to write this as 5s plus 3 upon s minus 1 into s square plus 2s plus 5. Now splitting into partial fractions. This one, because it is a linear factor, the coefficient on the top will be a constant. Now we have a quadratic. So the coefficient will be a linear bs plus c. So when we split into the partial fractions, there's a quadratic in s. So numerator has to be a linear in s. So bs plus c. Now we can equate the numerators. A into s square plus 2s plus 5 plus b times s plus c into s minus 1. So we need to find a, b, and c. So 3 conditions. First one, put s equal to 1. If you put s equal to 1, b plus c times 0 we get. So left hand side is 5 plus 3, 8 to a into 1 square plus 2 into 1 plus 5. So this is also 8. 5 plus 3, 8. This 5 plus 3, 8. So this implies that a is equal to 1. That's what we get. Next, a we found. Suppose I want to find now b or c. Easy trick for finding c. is put s equal to 0. If we put s equal to 0, b vanishes. And then we already know a, we can find c. So put s equal to 0. So we get 5 into 0 plus 3, and a times 0 plus 0 plus 5, and a is 1 from the previous result, plus b times 0 plus c times minus 1. So this gives 3 is equal to 5. 1 into 5, a is 1, 1 into 5 minus c. So this gives us that c is equal to 2. So c is equal to 2. A equal to 5 and c is equal to 2. And then let us find b. To find b, we can just equate the coefficients of s square. Coefficient of s square on the left hand side and the right hand side. All right, we are comparing these two, remember. So coefficient of s square on the left hand side is 0. On the right hand side, you have a s square, and also you will have b s square. That's all. You won't have any other coefficient of s square. So from here we get b is equal to minus a, which is minus 1. So s is sorry. Now, so the partial fraction a is 1, b is minus 1, c is 2. So f bar of s we can write as a is 1, 1 upon s minus 1, plus b is minus 1 minus s, c is 2 plus 2 by s square plus 2s plus 5. Now let's simplify further. I have to get into standard forms, mind you. For that, first write this denominator correct. We can write this as s plus 1 the whole square plus 2 square. To get into standard forms, numerator, I should have s plus 1. So what I'll do, I'll write minus of s plus 1. So I get minus s minus 1 plus 3. So minus 1 plus 3 will give me plus 2. So I have split this way. So 1 by s minus 1, then divided by the next term s plus 1 by s plus 1 the whole square plus 2 square. Then plus 3 by s plus 1 the whole square plus 2 square. So now these are standard forms. Now we can do it. Laplace inverse of this given function. This is Laplace inverse. I'll directly write the results. Laplace inverse of 1 by s minus 1 is e power t minus, now s is replaced by s plus 1. So s minus of minus 1. So e power minus t here. And this is cos s by s plus s square plus a square. So cos 2t. Simple. Next, this is sine. 3 comes out as constant. You have to multiply and divide by 2, and then this is sine, but s is replaced by s plus 1. So You have to multiply it by e power minus t sine 2t. So this is the result. So this is the result. We can simplify it further if needed, but we can stop here. Okay, so I covered a lot of problems just for practice before we could go to properties. But now let us move on to properties. So these are results, these are practice problems simply based on the direct formulae. Okay, and these three we have not used. Of course, if it is directly there, we can directly substitute and substitute this result. Now let's look at the properties of Laplace transform, inverse Laplace transform. Properties of inverse Laplace transform. Of course, some of them we have already used. Okay. Linearity property we have already used. In the above results. What it says is Laplace inverse of A times F1 bar of S plus B times F2 bar of S plus C times F3 bar of S will be A times Laplace inverse of F1 bar S plus B times Laplace inverse of F2 bar S plus C times Laplace inverse of so this is the linearity property. Next is the shifting property. Now, shifting properties, of course, we have also used this directly. So, if Laplace inverse of f bar of s is f of t, then Laplace inverse of f bar of s minus a, this we did, is e power at f of t. This we have already used in the problems that we have done. This was s shifting. Now we have a t shifting property also, right? F of t minus a. So that we'll look into. So if Laplace inverse of f bar of s is f of t, then Laplace inverse of e power minus as f bar of s. E power minus as f bar of s is f of t minus a for t greater than a and 0 for t less than a. This directly you can write this as f of t minus a times the unit step function. Sorry. The unit step function, which is also called as the Heaviside function. So we have done that yesterday. Laplace transforms of special functions. So unit step function. Laplace transform of unit step function is e power as minus as by s. So t shifting, Laplace transform of f of t minus a times the unit step function is e power minus as f bar of s. This is what we showed also, we proved. So inverse of this is what we have done today. So this is s shifting, this is t shifting, t minus a. Then change of scale. So change of scale property. If Laplace inverse of f bar of s is equal to f of t, then Laplace inverse of f bar of as is 1 by a f of t by a. Look at the shifting property from Laplace transforms, not the change of scale property from Laplace transform. See, change of scale property. There it was said that, you know, f of at will give 1 by a f bar of s by a. Now what we should do, replace a by 1 by a. If you replace a by 1 by a, I'll get f of t by a, and this a goes up and I brings down 1 by a f of t by a is equal to f bar as. So using that, we are doing this. F bar as is 1 by a f of t by. Then multiplication by s is derivative, if you remember. Now if Laplace transform, sorry, Laplace inverse of f bar of s is equal to f of t, and f of 0 is equal to 0, then Laplace inverse of s into f bar of s is derivative of f of t, because derivative of f of t, so Laplace, you remember this one, Laplace of d by dt of f of t, not inverse, the Laplace of this is s times f bar of s minus f of 0. So f of 0 is 0. So s into f bar of s inverse will be derivative of f of t. Now in general, Laplace inverse of s power n. So you're multiplying with nth power of s. This will be equal to the nth derivative with respect to t of f of t, provided these all are 0. F of 0 and f dash 0 up to the n minus first derivative of 0 are all zeros. Okay, because that's the general formula for multiplication. Multiplying by t power n. So Laplace transform of derivatives. So if you look at this result, the nth derivative of f is s power n into f bar s, then minus s power n minus 1 f of 0 minus s power n minus 2 f dash 0 minus s power n minus 3 f double dash 0 goes on to s power 0 f of n minus first derivative. So when you when we substitute, suppose all the derivatives at 0 are 0, then we are left with just this term. So from that, we have arrived at this result. So this result is a very important result. Of course, this condition is very important. So multiplication by s. Now division by s means integral. So Laplace inverse of 1 by s of f bar of s is integral 0 to t f of t or f of u du, where Laplace transform of f of u or f of t is this. So we are integrating. Similarly, suppose it's a division by s power n. So this will be integrals n times. f of u du du du. So this is n times integral. N times integration. The next property. So inverse transform on derivatives. So Laplace inverse of, okay, nth derivative of the function. Oh, sorry, nth derivative with respect to s. Laplace inverse of this is nothing but minus 1 to the power n, t power n, f of t. Once multiplying by t, we differentiate the transform, Laplace transform. So n times multiplying, we'll differentiate n times with minus 1 to the power n sign. So same thing in the reverse way, we get this. So Laplace transform on derivatives and Laplace transform on integrals. Laplace inverse on integrals. Integral s to infinity f bar of s ds. So this is division by t. One time integral is f of t upon t. Multiplication by t is derivative. Division by t is integral. So inverse also works like that. Last, this is an important theorem, many times asked. This is called as the convolution theorem. Convolution theorem. Now what this says is, if Laplace inverse of f bar of s is equal to f of t and Laplace inverse of g bar of s is equal to g of t, then the Laplace inverse of the product f bar of s into g bar of s is not just product of f of t and g of t. It is integral of 0 to t, now f of u into g of t minus u du. So of course, which is also the same as f of t minus u into g of u, depends on which one you want to choose. So convolution theorem depends on how you choose f and g. So this is denoted as, this is also denoted as F star G. Okay, so F star G is called convolution of F and G. So let's see how we use these properties in the problems. Hmm. So next set of problems based on properties. This is problem set 2 for inverse Laplace transforms. So find the Laplace inverse. In all these cases, find the inverse Laplace transforms. For the following. So here the more important thing is using the properties. So the first one, s square by s minus 2 the whole cube. Of course, this we can do purely by we can very easily do by partial fractions, but we will use properties. So using property of multiplication by s. Multiplication by s means we are differentiating. Okay, so let us do this. So now f bar of s is s square by s minus 2 the whole cube. So Laplace inverse of this f bar of s is Laplace inverse. I will write this as s times s by s minus 2 the whole cube. Now this, once you multiply with s, okay, then this is differentiating with respect to t of Laplace inverse of this one, provided, yeah, let us just look at this result. This of course multiplication by, now we don't know whether derivatives are zero, that we have to check, but assuming that the first derivative is zero of f of s, let us do that, provided f of t, first derivative of this transform is zero. F1 is transformation, the function for this. Okay. Next again, we will have to do d by dt. We'll simplify Laplace inverse of, I'll write this as s minus 2 plus 2. This will help me to not deal with that s again. 1 by s minus 2 the whole square plus 2 by s minus 2 the whole cube. So this is d upon dt. Laplace inverse of s minus 2 the whole square. 1 by, so this will give me e power 2t into 1 by s square is t power 1 by 1 factorial plus 2 times e power 2t times this is s minus 2 whole cube. So I get t power 3 minus 1 by 3 minus 1 factorial. So 2 now I have to differentiate this. 2 cancels here. I'm left with derivative of e power 2t times t plus t square. Now we can differentiate first function, keep the first function as it is and differentiate the second with respect to t, plus differentiate the first function keeping the second as it is. So taking e power 2t common, we'll get 1 plus 2t plus 2t 4t plus 2t square. So this is the Laplace inverse of the given function, which we can do using partial fractions for this one. It is not a difficult one. We can do it, but this is the easy route. Second, s plus 2 the whole square by s square plus 4s plus 8 the whole square. So how to do this problem? Now we can use standard techniques, or so let us see this. This f bar of s is s plus 2 the whole square by s square plus 4s plus 8 the whole square. So this is s plus 2 the whole square, and we can write this s plus 2 the whole square plus 2 square. 4 plus 4 8 the whole square. Now Laplace inverse of f bar of s is Laplace inverse of this. Okay. Now this one, replacing s by s plus 2. So it is multiplication with e power at s by s minus a. So this is s minus of minus 2. So this is multiplication of e power, multiplication by e power minus 2t times the Laplace transform of this function. So this made it easy to deal with. Now there are two s's, so we can write this as s into s by s square plus 2. Now multiplication with s means differentiating d by dt of Laplace inverse of s by whole square. Now this is a standard result. Let's go back. On the top in the first set of results, look at this 13th one. S by s square plus s by s square plus a square whole square Laplace inverse is 1 by 2a t sine at. So this is derivative of 1 by 2a. So 2 into 2, 1 by 4 t sine 2t. So e power minus 2t into 1 by 4, and now we differentiate derivative of t, keeping sine 2t as it is, plus keeping t as it is, differentiating sine, we'll get cos 2t. So 1 by 4 sine 2t plus 2t cos 2t. Okay. Of course, the same formula will go up. Okay, we can split this into, combination of this we can do, but that's difficult to comprehend and do that. So this was one easy method. How using properties we have simplified. Now we can alternatively do this by convolution. We will see this. So alternative using convolution theorem. We will apply convolution theorem from here, from this point. Okay. So Laplace inverse of f bar s is Laplace inverse of s plus 2 the whole square by s plus 2 the whole square plus 2 square the whole square. This is e power minus 2t, Laplace inverse of s square by s square plus 2 square the whole square. Okay. Now here we had split into s by s square plus 2 square, and then we did the differentiation here like this, derivative of this, and applied the result. Now here we can use convolution theorem. I will write this as e power minus 2t. Now this is Laplace inverse of s by s square plus 2 square into s by s square plus 2 square. Now this is convolution of two same functions. This is cos 2t. This is, convolution of Laplace transform of cos 2t. This is f bar s, and now using convolution theorem, we get this as integral 0 to t cos 2u, I'll write as u, and cos 2 t minus u du. Okay. Now cos c plus cos c cos d, or cos a cos b is, let's see, half of cos of a plus b. So that gives cos 2t minus half of, minus cos of a minus b plus cos of a plus b. Okay, so it is plus, so it doesn't matter. So cos of a plus b plus cos of a minus b du with respect to u. So half e power minus 2t integral with respect to u. So this is constant. So I get u cos 2t, the first integral, applied on u equal to 0 to u equal to t. Remember, don't confuse with t. Then this integral, this is a function of u. So we get minus sine u. No, integral of cos is sine. So sine 4u minus 2t upon 4. Again, limits applied on u equal to 0 to u equal to t. So I get half e power minus 2t. So once I substitute u as t, then u as 0. So I'm left with t cos 2t plus 1 by 4 times substitute u equal to t. So I get sine 4t minus 2t is sine 2t. Minus u equal to 0, sine of minus 2t. So I'll get 1 by 2 e power minus 2t, t cos 2t plus 2 sine 2t I'll get. So half sine 2t. Pull this out 1 by 4. Let's look at the previous answer. 1 by 4 e power minus 2. I'm taking half outside. So I'll get 2t cos 2t plus sine 2t. So this is the answer. Okay. So 1 by 4 e power minus 2t sine 2t plus 2t cos 2t. 1 by 4 e power minus 2t, 2t cos 2t plus sine 2t. Exactly the same answer. So what we have done here is we have used convolution theorem and then just did the integration. Here, instead of using convolution, we manipulated this as s into s by s square plus 2 square whole square. So this is derivative, and then we had to use this formula, which we had to remember. In this, we don't have to remember that formula, but we have to remember the convolution theorem. So this is an alternative method. All right, I'll stop here. Next class, we will have complete more problems, a few more problems, and then we are ready to move to initial value problems of differential equations and how using Laplace transform we can solve them. All right, I'm ending the class here.